Welcome, focused learners, to this explainer. Today, we are adopting a completely new approach to tackling your exams, something I like to call the photographer mindset. I want you to think about a professional photographer for a second. When they walk up to a beautiful scene, they do not just randomly point their camera and snap a picture hoping for the best. Absolutely not. They find the perfect angle, they check the lighting, and they meticulously frame their shot to highlight exactly what they want the viewer to focus on. As a Cambridge 9618 computer science student, you need to be doing the exact same thing with your exam answers. Just like finding that perfect camera angle, we are going to learn how to frame your responses to perfectly highlight the specific evidence that Cambridge examiners are practically begging to see. And today, our subject is a topic that literally trips up thousands of highly prepared students every single year: bitmap image file structures. We are going specifically into the weeds on pixels, file headers, and image resolution. So grab your notebooks, get comfortable, because we are going to completely transform how you approach these exact questions. Okay, let's dive right into this by addressing a massive mystery. Why do highly prepared, incredibly intelligent students constantly drop easy points on seemingly straightforward pixel, file header, and image resolution questions? To understand this, I want you to imagine two totally different students taking the exact same 9618 past paper. We'll call them Alex and Sam. Now, they both come across a question asking them to calculate the file size of a bitmap image based on its header and pixel data. Alex is the kind of student who completely overloads the answer with raw computer science facts. Alex's hand is cramping up writing a massive paragraph explaining the entire history of binary, the dictionary definition of color depth, and what a pixel fundamentally is. But Alex completely fails to analyze the specific scenario provided in the question. Sam, on the other hand, is rushing. Sam breezes right in, misses the specific command word, maybe the question explicitly said evaluate, but Sam just described, and completely ignores the strict constraints of the image resolution given in the prompt. Both Alex and Sam walk out of the exam hall feeling incredibly confident. They both think they crushed it, and both of them are absolutely shocked when results day comes and they've lost those easy marks. So why does this happen? What is the disconnect?
Well, what's really interesting here is the ultimate examiner alert, and we are getting this directly from the source itself. This isn't just a guess. This is a direct quote from the Cambridge Principal Examiner reports. They state very clearly, the classic mistake is providing generic answers, not specific to the question context. Always link every point to the given scenario. This is exactly where Alex went so terribly wrong. Examiners do not want a textbook regurgitation. They are not impressed that you can simply define a bitmap file header from memory. What they actually want to see is if you can take your deep knowledge of how a header stores metadata, things like file size, image dimensions, and color depth, and apply it to the specific digital camera or medical imaging scenario they just gave you in the exam paper. If the scenario is about a medical scanner, they care deeply about lossless detail and high color depth for accurate diagnoses. If it's a tiny graphic for a smartwatch interface, they care about extreme compression and low file size. Generic, one-size-fits-all answers will absolutely tank your score, no matter how technically accurate your baseline definitions are.
We can really see this dynamic play out by comparing two student approaches: superficial breadth versus analytical depth. The student who relies on superficial breadth is just listing random facts. They are throwing everything they know against the wall, just hoping something sticks and earns a mark. But the student demonstrating analytical depth is doing something entirely different, something that the Cambridge benchmarks actively prioritize and reward with top marks. To make this transition from superficial breadth to analytical depth, top-scoring students secretly use an answering framework called PEAL. That stands for point, evidence, explanation, and link. You make your specific point about the bitmap structure, you provide evidence directly from the exam scenario, you explain how, for instance, the file header mathematically dictates the image resolution, and finally you link it all back to the specific constraints asked in the question. When you do this, the entire nature of your paper transforms. It's like watching those brutal red pen marks turning into brilliant green check marks, simply because you shifted your framing from just knowing a lot of stuff to deeply analyzing the specific problem in front of you. Section 1. Core Assessment Principles. Think of this as the rules of the game. To stop losing marks, we first have to understand the specific cognitive domains the Cambridge 9618 syllabus is actually testing. The assessment objectives aren't just fluff in the syllabus document. They're the exact blueprint the examiners use when drafting the mark schemes. This excellently illustrates the three pillars of the assessment objective. The first domain is knowledge and understanding. This is your basic recall. Do you know what pixels, headers, and resolution are? But notice, that's just row 1. Mere knowledge isn't enough to get an A star. Row 2 is application. This is applying those principles to unfamiliar contexts. If they give you a weird scenario about a deep space satellite transmitting bitmap images back to Earth, you have to apply your knowledge to the constraints of that specific satellite. And finally, row 3 is analysis. This requires logical, structured reasoning and an evidence-based breakdown of the problem. This proves that just knowing the mathematical formula for image file size is only the starting line. You must apply it and systematically analyze the evidence to scoop up those final highest-tier marks. So the crucial takeaway here is that examiners are actively hunting for this specific type of analytical depth. Let's really break down this definition. It involves the practice of evaluating multiple solutions, analyzing trade-offs, and justifying decisions with context-specific evidence. For example, if a question asks you about the implications of increasing the color depth of a bitmap image, a student with analytical depth won't just say, well, the image looks better. No way. They will analyze the trade-offs. They will explain that while an increase in color depth improves the photographic realism and reduces color banding, it drastically increases the total file size, which might critically violate the limited storage constraints mentioned in the scenario. They will then justify their decision using that context-specific evidence. That is exactly what framing your answer like a top-tier photographer looks like.
Section 2. The technical methodology. This is where we talk about the method mark strategy.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, here is the 5-step procedural framework you absolutely must use for method marks. In Cambridge Computer Science, the final calculated answer is often worth only a fraction of the total marks. The bulk of your grade comes from the method you use to get there. Step 1. Deconstruct the question. Step 2. Extract relevant data. Step 3. Select your analytical framework. Step 4. Execute with clear notation. Step 5. Present with correct terminology. Imagine you are asked to calculate the size of an image. You must extract the pixel dimensions and color depth from the scenario first. Then, you select your mathematical framework, you show every single step of your working out with clear, readable notation, and you ensure you use terms like metadata and file header completely accurately in your final summary. Executing that framework requires a very specific algorithmic mindset. You can't just wing it. This means actively breaking the problem into logical chunks, selecting the right structures, and testing your logic rigorously as you go. Even if you are just answering a purely theoretical question about how a bitmap is stored in a computer's memory, you need to use step-by-step decomposition. You start by explaining that the file header is read first by the software to determine the dimensions and color mapping. Then, you explain how the raw pixel data is mapped sequentially into memory based on that color depth. By laying it out sequentially, like an algorithm, you are proving beyond a shadow of a doubt to the examiner that you truly understand the underlying mechanics of image processing and that you haven't just memorized flashcards. Specifically for bitmap images, your data interpretation skills must bridge the massive gap between raw binary representations and final calculated conclusions. Remember, at its very core, a bitmap image is just a giant grid of pixels, and every single pixel is represented by a specific string of binary digits. When you are interpreting data for a tough exam question, you might literally have to look at a hexadecimal representation of a file header, figure out the image resolution from those specific bytes, perform the necessary calculations to find the total file size in kilobytes or megabytes, and then draw an evidence-based conclusion on whether that file can be successfully transmitted over a network with a given restricted bandwidth. It's like a giant puzzle, and every piece is intimately connected. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at AceTheExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's get into the examiner traps and warnings and discover exactly what makes you lose points. Looking through years and years of performance data on the 9618 syllabus, the principal examiner reports reveal that there are exactly 3 massive traps that catch students completely off guard every single year when dealing with bitmap image structures. Let's make sure you never fall for these. Make sure you memorize these 3 pitfalls. Trap number 1, using the wrong formula or algorithm for the wrong context. It sounds simple, but under pressure, students constantly forget to divide by 8 when converting bits to bytes, or they accidentally confuse the formula for an audio file size with a bitmap image file size. Trap number 2 is incredibly common and devastating: forgetting to check boundary conditions and edge cases. This instantly limits the performance of your algorithm or logic.
If you are writing pseudocode to manipulate an image matrix, what happens if the image has a resolution of 0 by 0? What happens if the color depth of a specific pixel exceeds the maximum allocated memory buffer? You absolutely must check these boundaries. And trap number 3, which we've touched on, but it is so lethal it bears repeating, providing answers that are not specific to the given context. If the exam question is asking you about a simple black and white scanned text document, please do not write a generic sweeping answer about 24-bit true color processing. A fantastic way to bypass these traps entirely is to engineer a quick memory hack for yourself. When you're sitting in the exam room, sweating under the pressure of a ticking clock, you need instant, reliable recall. I want to challenge you right now to a quick speed exercise. You have 30 seconds in your mind to create a custom acronym for the factors affecting bitmap image file structures, specifically pixels, headers, and resolution. Maybe something like PHR, pixels hold resolution, or whatever weird phrase works for your brain. By locking in all the variables related to pixels, headers, and image resolution with a simple mnemonic device, you guarantee that you will systematically address every single component when evaluating a complex bitmap scenario. You won't leave those easy marks on the table just because you panicked and forgot to mention the metadata stored in the header.
Section 4. The winning formula. We are going inside the mind of a top-scoring candidate. This contrast perfectly highlights the fundamental difference in how students approach problem solving. An average candidate looks at a problem regarding, say, incredibly slow image loading times on a website, and they state one single generic solution. Reduce the image resolution. Boom, done. But a top-scoring candidate takes a completely different path. They consider multiple solutions. Reducing resolution, sure, but also decreasing color depth or applying different lossy versus lossless compression algorithms. They analyze the trade-offs of each. They will note that reducing color depth might create terrible banding artifacts in a photograph, which is a massive limitation if the image is meant for high-end digital art or e-commerce. Finally, they justify their final decision using context-specific evidence from the prompt. This directly mirrors how a top student evaluates algorithm quality overall by proactively identifying time complexity, space complexity, and the impact of those sneaky edge cases. To achieve this elite level of evaluative thinking, you must adopt the deconstruct, solve, evaluate problem-solving framework. Step 1. Rigidly identify the given information in the scenario. Step 2. Break the calculation or the logical process into clear, methodical steps. Step 3. Solve it systematically, showing all your working clearly on the page. Step 4. Check your answers for reasonableness. This is huge. If you calculate the file size of a single standard 1080p bitmap image and your answer comes out to 4 terabytes, stop right there. Check your working for reasonableness because you have almost certainly missed a crucial bit to byte or kilobyte to megabyte conversion somewhere. And finally, step 5. Make fully justified recommendations based on your mathematically sound findings. And when you're faced with a very specific type of question, comparative analysis. For instance, when you're asked to compare different bitmap structures, perhaps comparing an uncompressed high-resolution 8-bit image to a heavily compressed lower-resolution 24-bit image, remember that comparative analysis mandates identifying both similarities and differences. You can't just list a bunch of facts about image A and then a bunch of facts about image B. That's not a comparison. You must stitch them together with comparative connectives like whereas, conversely, or on the other hand. Support every single comparison with hard evidence from the header data provided, and most importantly, draw a firm conclusion about the relative importance based on the scenario's constraints, such as tight network bandwidth or limited physical storage capacity. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Take the photographer framework with you into your very next study session. Apply analytical depth over superficial breadth, meticulously frame your evidence, and remember that your exam success starts with how clearly you see the problem. Keep up the focused learning, and I'll see you in the next explainer.